All right, so in this video, I'm going to be going through pages 12 and 13 in the notes packet. So we just talked about domain and range, and we did that just visually looking at the graph. Now we're going to be talking about what insights can you glean from the equation itself. So sometimes there'll be moments where you'll look at the equation and some things will jump out to you, or hopefully eventually they'll jump out to you, where you'll be like, oh yeah, I know that this is not part of the denominator, or not part of the domain, sorry, and understand why. So there's kind of two main cases that come from the equation where something might not be part of the domain. You want to look out for any places where the denominator of any fraction is 0, or any place where the radicand is negative. So let's take a look at the first one. We have this function and we want to graph it. So if we go to our graphing calculator and we do my equals. So I recommend you do an extra parenthesis around the numerator and the denominator here, just to make sure you don't get mixed up, right? It's important that the numerator stays together and the denominator stays together as well. And so that is x plus 2 times x minus 1 and then put parentheses to close the numerator, divided by, and then in the denominator, we have x minus 2 times, oh, I want to put an extra parenthesis in there too, times 2x, is it 2x plus 1? 2x plus 1. And then if we hit graph, this is what it looks like. I'm going to change my window just to match the graph on the notes page so I can graph it more accurately. So if I do that, it's going to look like this. So something like, let me remember, graph the function in red. So it went kind of like that, and then like that, and then something like that. All right. And so what happens at the graph at x equals -1/2 and x equals 2? So remember, x equals -1/2, that is this line right here. And x equals 2, that is this line right here. So what happens there? Well, we notice it kind of, on one side of it, it goes up. On the other side, it goes down. There's kind of a wall there, right? Like the function is very clearly divided at that line. And same over here, it goes down over here and up over there. And the reason why that happens is because if we think about plugging those values into the function, right? If we try and find f of 2, then we're going to get 3 times 4 times 1 in the denominator, or in the numerator, right? Plugging into there, over 0 times 5. Well, that's 12 over 0, which is undefined, right? You can't divide by 0. Nothing times itself, or 0 times nothing, right? You can't multiply 0 by anything to get 12. So that's undefined. And so where the denominator is 0, the function is undefined, and you're going to get something called vertical asymptotes. We're going to spend a lot more time talking about asymptotes, but the very short answer is that they show up where the denominator equals 0. So that's why 2 has an asymptote. If you think about why -1/2 has an asymptote, well, if we think about 2 times -1/2 plus 1, that's going to be -1 plus 1. So -1/2 is going to make this part of the denominator equal to 0. So 2 makes this part of it 0, -1/2 makes this part of it 0. That's why we have our asymptotes there. So if we want to find the asymptotes, what you can do is you can think about, well, here's my two parts of my denominator, x minus 2 and 2x plus 1. And you can set them both equal to 0. You can say, well, what values are going to make that denominator 0? And then solve, and you get x equals 2 minus 1, 2x equals negative 1, x is equal to negative 1 over 2. And that's how you can get the values that make the denominator 0. If we're looking at this one here, if we graph it, which I will do so now, clear 2x plus 6 graph. Okay, so we see that it kind of starts there and goes that way. And so what's the domain of this? Well, we see visually the domain is negative 3 comma infinity, or x is greater than or equal to 3. Negative 3, that is. So if we're saying solve the linear inequality below, hold on. So we know that square roots cannot be negative, right? If you have a negative in the radical, you're going to have an imaginary result because nothing times itself. No real numbers, whether positive or negative, times themselves give you a negative number, because if the number is negative, then when you multiply it by itself, it becomes positive. So one way to figure out where this function is going to be defined, where this radical is going to be positive or non-negative, is we can write an inequality like this. 2x plus 6 is greater than or equal to 0. And then we want to solve this. We're going to subtract 2 there, or subtract 6 there. 2x is greater than or equal to negative 6, divide by 2. You get x is greater than or equal to negative 3, which is exactly your domain. So if you want to figure out the domain of a rational function like this, what you want to do, you want to figure out what values make the inside non-negative, and you can do that by setting up this sort of inequality in solving. All right, on page 13, so besides two things that come from the equation, there are also some places where the domain will be restricted by the context of the problem. So one case where this could happen is if a function is discrete, right? Not all functions are defined for kind of a range of x values. So if you look at example 1, right, we have this function here, where the function doesn't have an equation, it's just a set of points. We just know if you input 0, you output 1, input 1, output 2, and so forth. And so for something like this, your domain and your range, they're not going to be a range, right? They're not going to be an interval. They're not going to be an inequality. They're just a set of values. So here the domain is just defined for that specific set of points. Same with the range. And then just the notation for this, when we write the domain and range, we always order them from least to greatest, as you can see here, and omit any duplicates. So as you can see, we have kind of 0, 1, and 3, 1 here. But in the range, I just write the 1 once. If we look at example 2, so an online moss retailer sells sheet moss in specific quantities. You can buy 5 square feet for $33, 10 square feet for $60, 25 square feet for $129, or 100 square feet for $460. If we let x represent the square feet of moss being purchased, here's our function. And we know that you can't buy, right, like you can't buy, 15 square feet of moss. Right? You can only buy you can't buy 15 in one package. You would need to buy 1 5 and 1 10. But if we're assuming you're only buying one package, you can't choose your amount, right? You're limited to these specific quantities. So the domain of that function is just all of the possible square footage that you can buy, that being 5, 10, 25, and 100. And then the range, well, that's all of the possible kind of prices that you can pay. So 33, 60, 129, 460, and so forth. So sometimes you'll have a discrete function and you want to be aware of when is the function actually defined between the values and when is it just defined at those values. Another thing that can happen is you might be modeling something, and even though the function's domain is defined for specific values, it might not always make sense in the context of the situation. So we look at example 3, An airplane starts its descent at a cruising altitude of 40,000 feet. Each minute after it starts its descent, its altitude decreases by 2,000 feet. So meaning about what's the plane's altitude after 10 minutes? Well, if it starts at 40,000 and decreases by 2,000 feet per minute over 10 minutes, that's going to be 40,000 minus 2,000 times 10, which is 20,000. So what's going to be remaining is 20,000 feet. And then how long does it take the plane to touch down after its first descent? Well, if it's moving at a constant rate, after 10 minutes, it's covered to the 20,000 feet. It means it's going to take another 10 minutes to cover the next 20,000 feet. So we know that the total time to descent we can write as 20 minutes. We want to write a function that represents the altitude of the plane, t minutes after the plane starts its descent. I would say h of t is that 40,000 that we're starting with, minus 2,000 times the number of minutes that pass. And if we try and find the altitude after 30 minutes, well, that's h of 30, meaning that it is 40,000 minus 2,000 times 30. That's 40,000 minus 60,000, which is negative 20,000, meaning that 30 minutes after the plane starts its descent, the plane has an altitude of negative 20,000 feet. It is burrowed 20,000 feet into the ground, except for that doesn't happen. So no, this does not make sense. Planes stay above ground. At least that's the hope. And then for what values of t would this function make sense? Well, it doesn't really make sense for negative values, right? We want to start at 0 and work up. So we want to start with t has to be greater than 0. We don't want negative time values. But it also should stop once the plane lands, right? Once we have once those 20 minutes have passed and the plane is on the ground, we don't need the function to go any further. So this function, yes, we can define this line for all points, but it only makes sense in context for this much smaller set of points, right? We can't extrapolate beyond